I'm Avi Avital. The aim of the statistical process is to describe the data and to infer from the sample statistics to the population's parameter. While doing so, the statistical process is exposed to various errors and biases. I will try to give you the basic milestone of this fascinating journey to the land of statistics. It is important to acknowledge that statistics and methodology go together. After formulating the research question, the researchers should decide about the most suitable study design and could significantly reduce various biases, for example, the probability of obtaining false positive or wrong inference regarding the effectiveness and safety of a particular drug. This decision involves not only methodological and statistical consideration, but also ethical ones, since it affects the sample size. The main two designs are the between subjects and within subjects. Implementing the between subject design, each group is being exposed to one treatment, such as drug type or dose, and the control group is almost always needed. This design requires a high number of subjects aimed to overcome the individual variability. Most of the time, the easiest and the efficient strategy is to use a within subject design, known also as repeated measures. This design uses the same individual as a control and consequently reducing the variability that exists between different individuals. Therefore, it is increasing the probability to reject the null hypothesis and avoiding false positive, that is referred to as type 1 error, rejecting the null hypothesis while it's valid. The probability of making misleading claims may be also reduced by adopting blinding procedures like double-blind and randomization as part of the research planning and design. Before addressing the sample size calculation, I would like to introduce you with some important terms in hypothesis testing. The null hypothesis is the existing state and is marked as H0. Complementary, the H1 reflects the researcher hypothesis. There are two types of hypotheses, one tail, right or left, and the two tails. You can see that the difference between the hypotheses is reflected in the researcher assumption in H1. This illustration reflects a right tail hypothesis, meaning the researcher assumes that the experimental manipulation will bring a bigger outcome compared with the null hypothesis. We can see the test statistics that is calculated from our sample is trying to reach the rejection zone, the alpha, and to allow the researcher to suggest an alternative hypothesis to the existing state, which is the null hypothesis. We have four states to discuss as part of H0 and H1 relationship. The first one is the alpha, known also as type 1 error or significance level, supporting the alternative hypothesis when the null hypothesis is true, false positive. The researcher is free to decide the risk for making this error, and usually it doesn't exceed 5%. The second one is beta, known also as type 2 error. It reflects less severe mistake, not supporting the alternative hypothesis when the alternative hypothesis is true, false negative. 1 minus alpha reflects the confidence interval, not supporting the alternative hypothesis when the null hypothesis is true. And the last state is 1 minus beta that reflects the statistical power. The null hypothesis is truly false, and we are able to reject the null hypothesis. This is the aim of the statistical process. The actual distance between mu0 and mu1 is the effect size. Once the experimental manipulation is significant, it will lead to a bigger distance between H0 and H1, thus increasing the effect size and the probability to reject H0 and move to H1. Increasing the sample size can affect the probability to reject the null hypothesis. For a given alpha level, we can stay with H0 using a sample size of 100. Or, just by increasing the sample size, we can reject H0 with a significance level less than 5%. Similarly, the increased n reduces the variability by reducing the variance or standard deviation and changes the distribution shape to be more homogeneous. Thus, increasing the sample size is leading to a lower probability to make beta error and consequently increasing the statistical power, which is 1 minus beta. By now, you should realize how important it is to determine the sample size prior to statistical decisions and inferences. To calculate the sample size, there are some free online calculators available and easy to use, but you can do it yourself. Let's use the following example. We need to calculate the sample size for examining the number of patients that will not respond to methylphenidate treatment for ADHD. First, we will decide on confidence level of 95%, which corresponds to alpha of 5%. And according to the z-score table, the z-value is 1.96. Alternatively, we can use smaller alpha such as 1%. Next, we will hypothesize that half of the population that is treated with methylphenidate do not respond to it. This is the default for the population's proportion estimate. If we have valid proportion coming from the literature or any other survey or preliminary result, we can obviously use it instead. Entering the data into the equation with epsilon reflecting a 5% probability of error yielded a result of 384.16. This result should be round to a higher whole number, meaning 385. Having the sample size, we would also like to calculate the confidence interval that estimates the error margins between the sample values and the population values. It is important since the statistical deed is about inferring from the relatively small and finite sample to the infinite population. For example, we measured that 95 out of 120 patients suffer from infection during hospitalization. What is the real proportion of those suffering from infection during hospitalization? Or what is the confidence interval? This time we will take a higher confidence level of 99%. From the table, we get z-score of 2.58. Using the equation of confidence interval, the result is 10%.71. It means that the estimation in our sample is plus minus 10%.71 away from the real value in the population with only 1% chance that we are wrong. Okay, so what next? After the research was conducted, we should decide which statistical test should be carried out. The study design, the measurement scale, available sample size, and of course the distribution are the most important considerations. It's easy to examine the distribution of each continuous dependent variable in the research by line graph. If the distribution doesn't look like a bell shape or Gaussian one, it has a non-homogeneous variance that can give rise to type 1 error. If the sample size is lower than 30, or the distribution is not normal Gaussian, but rather one of the other common distribution, then we should use non-parametric tests such as Wilcoxon and Mann-Whitney for 2 groups, or Kroskal-Wallis and Friedman test for more than 2 groups. Otherwise, the preferred parametric tests are allowed, such as t-test and different types of ANOVA. As a general rule, we should prefer a factorial design over 2 groups. The use of more than one independent variable will enable better face validity, which is the inference power to the population through the interaction effect, thus reflecting the real-life circumstances of neuropsychopharmacological and other physiological processes not being governed by one factor but rather by interacting ones. For example, drug combination, dose-dependent effect, and many more. Therefore, using ANOVA and not t-test, and definitely not a series of t-tests that inflates the type 1 error rate. For examining differences between each pair of groups, we should use post-hoc tests such as Bonferroni or Chaffee. So to sum up, first we need to formulate the research question and hypothesis based on the existing literature and of course adding scientific merit. Next, we should choose the research design, preferring the factorial one, and if possible, to incorporate a within-subject factor such as follow-up along a trajectory. In the next step, we will calculate the sample size needed for obtaining sufficient statistical power. Be aware of artifacts that may stem from exceeded sample size. In the fourth step, after obtaining the study's results, we need to examine the distribution shape of every continuous measure. In the fifth step, we should decide as for the suitable statistical test, which actually stems from the previous steps. And the next step is hopefully a significant publication. I hope that this short presentation was useful, and I encourage you to attend to the ECNP's schools and seminars to get more comprehensive training. Thank you and good luck.